All right, guys, nomenclature is still in our sights for the day. I know there's a lot of nomenclature that we've done already, but now we got to do a lot more. As I said before, the rest of the nomenclature is really based on the 22 basic polyatomic ions that we talked about last time. And you'll see that as long as you really know the names and formulas of those polyatomic ions, you can think about the formulas and names of other things that involve those ions. And the vast majority of the rest of nomenclature involves those ions. There's going to be one exception. And the exception is binary molecular compounds. Up to this point, we've talked about ionic compounds, and we haven't really defined the phrase ionic versus molecular, and we'll do that here in a second. But binary molecular compounds does have a different set of rules, although those rules are the ones that you've been thinking about in the back of your head since grade school, like carbon dioxide. Another example would be carbon monoxide or diphosphorus tetraoxide, things like that. And so that's binary molecular compounds. That'll be the last thing that we do. Hopefully we'll be able to get to that today. But the rest of the stuff really does involve the polyatomic ions that we started with yesterday, or last time we were together. So what I want to do today is get right back into that. And we're going to go from polyatomic ions to acids, and then acids to acid anions, and then acid anions to hydrates, and then hydrates after that we'll do binary molecular compounds. All right, so let's get rolling. Okay, so we want to start with acids, and acids are compounds that form H3O plus when reacted with water. And what that means is that it has to have an H plus ion, a hydrogen ion in the molecule. And so what I want to do is I want to give you an example of just a couple of acids that don't involve polyatomic ions. Okay, here's some acids that are neutral compounds formed from a hydrogen ion plus some other halogen-based anion. So it is like an ionic compound in the sense that you can think of them in terms of having a hydrogen ion and an anion from the halogen group, but it is actually a molecular compound. And what we haven't done yet is we haven't talked about the difference between an ionic compound and a molecular compound. So before I name those, I want to do that real quick. A molecular compound, first of all, it has all, let's say this, it has no ions in it. And you can tell that it's a molecular compound because it's made from only the non-metal elements. And so if you think about a periodic table, remember that the non-metal elements are right here. And so if it's a compound that is made from atoms that are only in this part of the periodic table, but this does include hydrogen, then it's a molecular compound. And so some examples would be carbon dioxide, Dinitrogen pentoxide, something like this. I mean, we can make up a lot of these compounds. Some of these exist, some of these don't exist. These are all compounds made from only these atoms. That's not a compound, that's a molecule, that's not technically a compound, but it would be molecular. Here's another example, water, that's a molecular compound. Okay, then ionic compounds. They're made from metals plus a nonmetal. So if you think about something like sodium chloride, chlorine comes from over here in the nonmetals, but sodium is one of those alkali metals. And so you can identify ionic compounds by the fact that it's made from a metal or a nonmetal. Another way is that you'll see it could have polyatomic ions. So here's an example of a compound, ammonium acetate. It's made from one ammonium and one acetate, which are all non-metal atoms. Everything in those compounds are non-metal atoms. Except you see them presented in the formulas that indicate that they are actually the polyatomic ions. If they weren't presented as polyatomic ions, then we would do something like this. CHNO, and we'd say C2H7NO2. There's the difference. If I just write C2H7NO2, then that's indicating to you that it's just a group of nonmetals that form a compound. But because I left the formulas of the polyatomic ions intact in ammonium acetate, that's the clue to you that I'm actually dealing with an ionic compound. So this would be the molecular compound, made from exactly the same atoms in exactly the same numbers, but it's not the same compound. Okay. So look for patterns. The pattern to look for is whether or not the formulas are represented exactly as the formulas of the polyatomic ions are represented. Except remember, when we write ionic compounds down, we don't write their charges down. So let's go back to acids. We were talking about acids, and we defined acids as substances that make H3O plus in water, and I want to show you how that works. The hydrogen ion reacts with the water, and you're left with the counter ion, and the H plus ion, the hydrogen ion, is now part of the water structure, and it becomes actually a new thing. This is hydronium ion. Hydronium ion. Okay, and so you know that this is an acid. How can you tell that this is an acid specifically? Well, notice that it starts the formula so this indicates to you that it's an acid. All right, so we don't want to get too far down the road of chemical reactions because we haven't actually done that part of the course yet. And so suffice it to use this example. When we talk about acids in the sense that they have an H plus ion, we have to remember that it's actually a molecular compound that essentially behaves as if it were ionic. So it really is, chemically speaking, an ionic compound, but if you really dig into the bonding, which we haven't done anything with yet, turns out that it's bonding like a molecular compound. So at the end of the day, an acid is something that has a hydrogen ion in it that can react with water to form hydronium ion. In other words, it's got you'll notice that because it has hydrogen in the formula, and that formula starts with hydrogen. It's really a molecular compound, and you can use your definition of a molecular compound to decide that. But it actually behaves as if it were a ionic compound, because that H plus ion comes off and then does reactive. And let me, someone was bugging me. There we go. It behaves as if it were an ionic compound. So the question is that ionic? And I'm not sure what the question means by that. So can you elaborate a little bit on that? Yeah, the last word is ionic. I'm getting a little sloppy with my handwriting. It's a molecular compound that behaves, and behavior is a chemical property. It's not really an official chemical property. It's just, what I'm saying is that if you mix it in water, HCl acts as if it has a hydrogen ion, and that hydrogen ion then attaches to the water and forms a new compound, and that compound itself is an ion. It's called the hydronium ion. So it behaves as if it were ionic. So what are these acids again? Let's look at the different acids that we already wrote down. So HCl, HBr, HI, and HF. This is hydrochloric acid. This is hydrobromic acid. This is hydroiodic acid, and this is hydrofluoric acid. Okay. Now, there technically is a rule about naming. These are called binary acids, and they're binary acids because they have only two different types of atoms in them. There's technically a rule. The rule is you take the name of the anion and you instead of bromide, you change bromide to bromic, and you add the word hydro and acid to it. But there's only 4 of them. And so the reason why I don't really talk about the rule with naming them is because there's only 4 of them. And so there's a couple of different steps to the rule. Take the anion name, remove the suffix, add ic acid, and stick the word hydro in front of it. You know, by the time you've memorized 3 different aspects of a rule, you might as well just memorize 4 different names. And the naming pattern is essentially the same. Hydrochloric, hydrobromic, hydroiodic, and hydrofluoric acid. Now, so just memorize these names like you would any other species that you just had to memorize. What I want to do is I want to specifically draw your attention to these 3. Because at some point you want to be able to identify strong acids versus weak acids. And there's going to be 7 total strong acids, and every other acid will be considered a weak acid. And the reason I'm calling out these 3 acids is that these are 3 of the 7 strong acids. So this is a strong acid. This is a strong acid. This is a strong acid. And at this point in the course, we just don't have the chemical understanding to really talk about why it's strong and what that means. And so we'll talk about that later on in the course. What we need to do right now is just memorize that these 3 are strong, that there's going to be 7 strong acids total. And all you have to do is be able to identify them as such. Okay, so these are 4 of the binary acids. These are the only ones you have to know in this course. And so you kind of just have to put those in your brain. But also at the same point, I want to point out those 3 are strong. And so let's talk about the other types of acids, the oxo acids. So let's take a look at these. Look what I did. And this is going back to why polyatomic ions are so important when it comes to nomenclature. Look at the different acids that I've written down. They all involve polyatomic ions that you guys should have memorized. They all involve these polyatomic ions. And in fact, it's almost as if you created an ionic compound using cross-down method for these acids. And so let's take a look about how we would use, before we get into the naming of this, how we would use cross-down method for polyatomic ions. So I want to leave that there just for a moment, and I want to come out and show you what I mean by that. Let's use sodium and nitrate as an example. We've already learned how to make ionic compounds from monatomic ions. And making ionic compounds is exactly the same thing when it comes to polyatomic ions. If I said, what's the formula for sodium nitrate or lead 2 sulfite, then we would do the exact same thing that we've done before when it comes to constructing the formulas of ionic compounds. I'm going to write down the formulas of the 2 ions and decide what are the ratios in which the ions appear in order to be neutral. I know that I'll need a sodium ion. I know that I'll need a nitrate ion. How many of each of these do I need? I need 1 and 1. The same thing would happen with lead 2 ion and sulfite. I would need 1 and 1. The only difference comes if we need if we need 2. What about calcium acetate? So the calcium ion is Ca2 plus, acetate is C2H3O2 minus, and you see that I need 2 acetates to balance the 1 calcium. So the only difference is because it's a polyatomic ion, I'm going to put it in parentheses and then tell the reader that I need 2 of them. That's the only new thing. So the only new thing is that we're going to use parentheses around polyatomic ions. Just a couple of more examples real quick. So what about, let's do magnesium phosphate. Well, that comes from the magnesium ion, which is Mg2+, and phosphate, PO4 3-. And so how do I do that? What's the formula for that? Mg, how many of those do I need? 3. I don't use parentheses in this case because this is a monatomic ion. However, I do need 2 phosphates to balance that out. It's a polyatomic ion, so I'll put that in parentheses. So the formula for magnesium phosphate is written like this: Mg3 parentheses PO4 end parentheses 2. We're going to do the same thing for acids. So if I'm going to have an acid that's made from the sulfate ion, and I want to add the requisite number of hydrogen ions, then I'll create the same type of formula for as if it were a polyatomic ion. And so you're identifying it as an acid because it starts with a hydrogen. And we're going to be able to name it based on the fact that it has a polyatomic ion that we're familiar with. So there is a little bit of a new thing that we talked about, although it's not really new. It's forming ionic compounds from polyatomic ions. It's done exactly the same way. The only difference is we need to use parentheses around the formulas for polyatomic ions if there's more than one. Look at lead-2 sulfite. Since it's 2 and 2, remember I won't use 2 parentheses 2 for lead-2 sulfite. They just cancel out. So the formula for lead-2 sulfite is PbSO3. No parentheses needed there. Where does the 2 come from for the H and the PO4 2? This one. It's like the cross down. Remember, this is overall neutral. And so there's nothing that's new that's happening here. I've got a 2+ ion, and I have 3 of them. That's 6+ total. The phosphate is 3-. I'm going to need some quantity in order to get 6-. What's that quantity? Well, 3 times 2 is 6. I'm still just using this old cross-down method to figure out the formula for the ionic compound that is magnesium phosphate. It's just a little bit more of a situation in the sense that now I have to do that with a polyatomic ion instead of a monatomic ion. Same thing with acetate, right? With calcium, with magnesium acetate, C2H3O2-. I have to have 1 magnesium and 2 acetates to get a compound that's overall neutral. So this 2 comes from the fact that the charge on magnesium is 2+, right? It always makes the total charge on the ionic compound neutral. So the same thing is working with acids, right? The overall formula of an acid is neutral, and you would build the formula the exact same way you would as if it were an ionic compound. Remember, it's not technically an ionic compound, it just behaves that, chemically speaking. Not only does it behave that way when you put it in water, it acts as if it has H+ ion, but it also does that in terms of its formulas. It forms the formulas of the compounds as if it were just ionic. And so let's go back to those oxo acids. Let's rewrite all of those down. And let's think about how that works. So we did HNO3. We did H2SO4. Let's go back to this one. I'm going to write it down here. I want to make the acid from phosphate. And phosphate is PO3, or excuse me, phosphate is PO4, 3 minus. And I keep writing 3. PO4, 3 minus. So how many H pluses do I need in the formula? Well, that's a good question, and I'll address it here just one second. I need 3 H3 pluses to balance out the 3 minus charge. That's why the formula for this acid is H3PO4. So as an aside, the question was, will the parentheses ever be on the first? Well, it will, because we do have one polyatomic ion that's a cation, ammonium. So ammonium ion is NH4 plus. What if I had ammonium sulfate? Well, ammonium sulfate would be the compound that comes from ammonium ion and sulfate ion. And so we're still going to form the formula the same way. I need an ammonium ion in the correct numbers to balance out the sulfate. That means I need 2 of them. I only need 1 sulfate, so there's no formula, there's no parentheses around the sulfate. So the answer to the question is, yeah, you'll need parentheses on a polyatomic ion if it's a cation, but the only cation that we know or have to memorize is ammonium ion. So it does work the same way. Okay, so let's go back to the naming of these acids. Carbonate is H2CO3. It's got a 2 minus charge, so it needs, our carbonate is CO3 2 minus. So the acid from it would be H2CO3. It's got a 2 minus charge, so it needs 2 of them. What about these guys? HNO2, remember the nitrate and nitrite have the same charge. Sulfate and sulfite have the same charge. Phosphate and phosphite have the same charge. So there isn't any sort of difference in the number of hydrogens, it's the number of oxygens that change. It's the same thing for these guys, right? HClO4, HClO3, perchlorate, chlorite, and hypochlorite all have the same charge. So you only need 1 hydrogen in order to balance out the formula to make it neutral. Okay, so let's name them then. And here's the rule. And I'm going to write the rule down and then I'm going to erase it. Eight ions become ic acids and ite ions become os acids. It's not necessarily a rule. It is, I'm going to present it as a rule. You'll see where there's some issues with that if you're paying attention. But it is something that you can use to remember what are the names of these acids. How do you name them? 8 ions become ic acids and ite ions become os, O-U-S acids. So let's see how that works. What is this? This is the nitrate ion. It's the acid that's formed from nitrate. So it's an 8 ion. So if I'm dealing with the acid that is formed from an 8 ion, it becomes an ic acid. So this would become nitric acid. So I'm taking the root of the polyatomic ion's name, nitrate. I'm removing the suffix, and since it's an 8 ion, it becomes an ic acid. And so I'm adding ic acid at the end. So sulfate becomes sulfuric acid. Phosphate becomes phosphoric acid. Carbonate becomes carbonic acid. And what about nitrite? NO2 minus, the acid formed from nitrite. Ite ions become os acids. So it goes the same way though. This would be nitrous acid. This would be sulfurous acid. This would be phosphorous acid. And remember, there is no carbonite outside of Star Wars. How does this work with the halogen-based anions? Well, here's chlorate, so that becomes chloric acid. Here's chlorite, so it becomes chlorous acid. Well, it works the same way with hypochlorite and perchlorate. Hypochlorite is an ite ion, so it becomes hypochlorous acid, as well as it becomes perchloric acid. So again, the rule is 8 ions become ic acids, ite ions become os acids, and it really is just taking the root of the name of the polyatomic ion, taking off, removing the suffix, and adding on the new suffix and the word acid to do it. And so I wanted to then, let's figure out we learned 3 strong acids already. Here are another 2, 3, 4. Oh, did that wrong. 3, 4. So what are the 7 strong acids again? Let's rewrite them down. HCl, hydrochloric acid. HBr, hydrobromic acid. HI, hydroiodic acid. HNO3, nitric acid. H2SO4, sulfuric acid. HClO4, perchloric acid, and HClO3, chloric acid. Those are the 7 strong acids. Once you are able to name the acids correctly, it's not really a leap to then say whether or not it's strong. If it's not strong, then it's weak. So all of the rest of the acids are weak. And so let's just do this example again real quick. We did these. What about these though? What about the acid here? HBrO3. This is bromate. So this one would be bromic acid. Well, what's the formula for hypobromous acid? Well, hypobromous acid must come from the hypobromite ion. So I want to write that down, BRO minus. How do I write the formula? Well, I need to add H plus until it's neutral. So that would be HBRO. Yeah, and so this is how we go in reverse. So going right back to the very beginning, it is a molecular compound, but in almost every single way, it behaves as if it's an ionic compound. And we're going to treat it that way going down the road. So again, I hope at this point what you're seeing, and I'm not going to write down the other ones, but look, there's HBRO4, there's HBRO2, there's HIO4 and HIO3. All of those are just exactly the same way. You name them the same way as you do these four. There's a hypoiodic acid, or excuse me, there's a hypoiodous acid, a iodous acid, an iodic acid, and a periodic acid. Just like the naming for the chlorine-based anions is exactly the same. So there are these other acids that you have to know. I'm not writing them all down. I did use some examples here. Bromic acid, hypobromous acid. And so I might ask you a trick question, and the trick question might be like this. What is the formula for hypoiodic acid? Well, if it's a hypoiodic acid, it must have come from hypoiodate, because 8 ions become ic acids. Why is it a trick question? There is no hypoiodate. There's only a hypoiodite. So that's why I give you an example of, well, here's one thing that doesn't work. There's no hypoiodic acid because there is no hypoiodate. Yeah, so the question is, how do we memorize which ones are strong and which ones weak? You just memorize them. 3 of them are binary acids, HCl, HF, or excuse me, HCl, HBr, and HI. And the other 3 they're all 8 acids: nitrate, sulfate, chlorate, and perchlorate. And so you just kind of, yeah, there's 7 total. So there's 7 total. Okay, and so let's do acid anions. HSO4. H2SO4 is, what's the name of this again? Let's think about it. This is from the sulfate ion. 8 ions become ic acids. So this must be sulfuric acid. Exactly. One of the things that I said about these acids is they can behave as if they have the properties of an ionic compound. So we know that I had 2 H plus ions to balance out the 2 negative charge from the sulfate. But what if I gave up only 1 of those H plus ions? If I give up 1 H plus ion, and I leave 1 in the formula, I'm left with this thing. This is an acid anion. It's, in other words, it's the anion formed from an acid after it gives up a H plus ion. So we can write a little chemical reaction that says, here's the acid. What would be the formula left if I took away 1 of the H plus ions? So let's just make sure that we're all on the same page here. If I take away 1 of the H plus ions, then I'm left with 1 of them there. The charge on these reactions have to be balanced. I know that I haven't really talked about that yet. That's not the important part, but it'll be helpful in establishing the formula of an acid anion. If I do the cross down and I only have 1, what's the new charge on the species? Well, I've balanced out 1 of the minus charges, but not the other one. So it still has a negative charge. That's why it's called an acid anion. So it's an anion that forms, so it does have a negative charge. It forms when one of these oxo acids gives up a proton, gives up an H plus. So we need a name for this. We need a name. This is the next bit of nomenclature. We need a name for these types of ions. So you might say, oh, Eric, you told me there's only 22 polyatomic ions that I have to remember. And now you're telling me there's some more? There's H2SO3 as well. It could give up a proton, an H plus ion, and that would leave me with HSO3 with a negative charge. I got to name this one too? All right, you do. But again, the names come directly from the names of the polyatomic ions. What I said at the beginning when we learned the names of the polyatomic ions is that that's what's going to determine your success in nomenclature, is whether or not you know them. We just saw that with acids. This is sulfurous acid because it's sulfite ion. This is sulfuric acid because it's the sulfate ion. So as long as we knew the rule, ic acids become, or excuse me, ate ions become ic acids and ite ions become os acids, as long as we knew that rule, then we can come up with the name sulfuric acid or sulfurous acid. Now, the same thing applies for these acid anions. As long as you know the name of the compound, or the name of the polyatomic ion, then you know the name of these acid anions. It's not actually that strange. This is hydrogen sulfate. This one is hydrogen sulfite. So if you know that this is sulfite and you know that this is sulfate, all you're doing is telling the reader how many hydrogens there are with it. Now, remember, if there's 2 hydrogens with it and it's neutral, this is an acid. It's not an acid anion. So you name it that way. But if it's got a negative charge, then you just tell the reader how many hydrogens go along with the polyatomic ion. So that means we've got some other ones to do, right? What's the formula for hydrogen carbonate? Well, So the question, so in the case of the sulfur version, that's true. So the question is, 3 is I and 4 is 8. That's only true for sulfate and sulfite, right? It's not true for nitrate, nitrite, and nitrate. It happens to be true for phosphoric acid, phosphate, and phosphite, but it's not true for carbonate, right? What's the formula for carbonate? The formula for carbonate is CO3 2-. So what's hydrogen carbonate? Well, hydrogen carbonate has an H+ ion attached to it, and so that means the charge went from 2- to 1-. So it's not HCO4-, right? Because 8 doesn't mean 4 and I doesn't mean 3. It just happens to do that in the sulfur and the phosphorus versions. So hydrogen carbonate is HCO3-. What's dihydrogen phosphite? What's dihydrogen phosphite? How do I put this one together? Well, what's the formula for phosphite? PO3 3-. Then what does dihydrogen mean? How many hydrogens does dihydrogen mean? Dihydrogen means 2 of them. But now I have to change the charge. The charge isn't 3- anymore. I've added 2 plus charges to it. So if I take +2 and subtract 3 from it, I get -1. And so the new charge is -1. There's dihydrogen phosphite. Well, what would this one be called? HPO4 2-. What's this one called? Hydrogen. And what's this one? What's the basic, what anion is that? Hydrogen phosphate. So that's how these acid anions work. There isn't a dihydrogen carbonate because dihydrogen carbonate is an acid. It has a name already, carbonic acid. If I lose another proton from hydrogen phosphate, if I take another hydrogen ion away, I'm left with PO4 3-. We already have a name for that as well, phosphate. If I add another H+, H2PO4, now it's just a negative charge. That's dihydrogen phosphate. Okay, any questions about that? Again, that's really straightforward. I think if you know the names of the polyatomic ions, then you should be okay here. And it really is just about thinking about how these charges balance with each other. Okay, 2 more sections and then we're done. A lot of nomenclature to think about. At the end of this, I'll ask you a question. I want to get your opinion on something. Okay, this is going to be a good transition from ionic compounds into binary molecular compounds. Hydrates are the last section of nomenclature involving ionic compounds. Hydrates are ionic compounds that have water stuck to them. And I'm going to use the phrase, I'm just going to put that in quotation marks and say they're stuck. Briefly, what happens is that when you form an ionic compound and you isolate it into a solid, sometimes you can't do that right away without getting water stuck to the ions. Now, you can drive this water away through different processes, but sometimes you can't do it right away without having some water stuck to them. So we want to come up with a way to name these hydrates. And so let me give you an example of what I mean. Let's have sodium nitrate. And the way that you would write the formula would be to write a dot this means it's stuck. It's not actually part of the ionic compound, but it's stuck. Each one is called a water of hydration. So you tell the reader with a dot, and the dot means that there are some waters of hydration stuck with the ionic compound. The dot signifies this aspect of being stuck and not actually part of the formula. And so this is a hydrate. How do you name this compound? Okay. Again, if you know the names of the polyatomic ions, naming these compounds becomes trivial. What's the name of this compound without the waters? NaNO3. It's sodium. Let me change colors. NaNO3 is sodium nitrate. Okay, so how would you name its hydrate that has two waters of hydration? It's quite straightforward. We tell the reader how many waters there are. So instead of sodium nitrate, it becomes sodium nitrate dihydrate. It's that straightforward. It's a hydrate. We're telling the reader how many waters of hydration there are. Again, if you know the names of the the polyatomic ions, then you can come up with the name of the ionic compound in a straightforward fashion. If you can come up with the name of the ionic compound in a straightforward fashion, then you can come up with the name of the hydrate in a straightforward fashion, because all you're doing is telling the reader how many waters of hydration there are by using a prefix and the word hydrate. So let me give you an example in the reverse order. What is iron? What's the formula for iron 3 sulfite trihydrate? So we got a lot of work to do. I think most of the work involves identifying the polyatomic anion sulfite, SO3 2-. We know that iron 3 is a monatomic ion of iron with a 3+ charge. Trihydrate means that whenever I figure out that formula, I'm going to add 3 waters of hydration to it. So what's the formula for iron 3 sulfite? That's the real challenge. And again, the challenge with that is knowing the formula for sulfite so that you can do the cross-down method. How many irons do you need? 2. How many sulfites do you need? 3. And then let's add the waters of hydration. So I hope at this point you're starting to see that everything really does build. Once you have those basic skills that you use for monatomic ions, everything does build on the formulas and names of the polyatomic ions, those 22. And so what about these prefixes here? What do we use for 1? Mono, 2, di, 3, tri, 4, tetra, 5, penta, 6, hexa, 7, hepta, 8, octa, 9, nona. So you could have something like this. What's the formula? What's the formula for ammonium? Let me make some room here. Let's do ammonium phosphate heptahydrate. Again, heptahydrate. Hepta is 7. So that should be straightforward. 7H2O. Ammonium phosphate. The challenge here is figuring out phosphate. What's that? PO4, 3 minus. Ammonium is another polyatomic ion, so that one's a little bit of a challenge as well. But now that I have written down the formulas of the 2 polyatomic ions, I can come up with the compound. NH4, how many of those do I need? I need 3 of them, so I need to put them in parentheses. How many phosphates do I need? PO4. I only need 1 of them, so I don't need any parentheses. And now I add my 7 waters of hydration. So there's ammonium phosphate heptahydrate. It's always water, right? That's why it's not such a huge leap into anything crazy. A hydrate always has waters of hydration. And so go back, rewind the video a little bit. I think it's about 8-9 minutes at this point, and go back to the basic definition of what a hydrate is and how we put together the formulas. It's always a water of hydration. Okay, and so that's it. That's it for hydrates. That's all there is to it. Again, the bottom line is figuring out the formulas of these polyatomic ions. You've got to know them. If you don't know them, you can't put any of this nomenclature together. Well, so why I said this was a good jumping point for binary molecular compounds is this. This is the last bit of nomenclature. In a binary molecular compound, it has a formula like this, AXBY. So it's made of 2 different atoms. It's a molecular compound, so what does that mean? A and B must be what? Non-metals. They must be non-metals. That's what makes them molecular compounds. Why was hydrates a good jumping off point? Because we're going to use these prefixes again. Tetra for 4. This is where the differences start to come from your common experience. Pent for 5, hex 6, 7 is hept. It's not sept. That's the common mistake, right? Is sept for 7 is not the way we do it in chemistry. It's hept. Oct, and 9 is non. The only challenge is this. Sometimes I drop the A. Sometimes I drop this A. And it's going to take some experience to figure out when I drop it. It's typically I drop it when I am putting it 2 vowels together. So an A-O would not go together. So it's not going to be tetraoxide, it would be tetroxide. This would be the way to do it. So we drop the A when it comes before an O. So let's put this together and let's see what I mean in this binary molecular compound nomenclature. Here, let's start off with an example that you guys all should know from everyday experience. How do I put this together? It works like this. Prefix, and here are the prefixes. Atom name, that goes for A, then it's prefix, and then anion name for B. So how do I name CO2? Okay, well, what's the only exception to this rule? The only exception is here. We do not use mono in this position. We let it be understood. So how do I put together the name for CO2? What's its name? Well, I would use a prefix, but because there's only one carbon, I would use the prefix mono, and that's the exception. I don't use mono in that position. So I'll just go to the next part, which is the atom name. Carbon. What's next? The prefix. What is the prefix that I need to use? Well, there's 2 oxygens, so I need to use the prefix di. Then what's the atom B? What's its name? Well, the atom is oxygen, but we don't use the atom name, we use its anion name. Even though it's a binary molecular compound, it's not made of ions. The naming of the molecular compound involves the same words as the anion. So this can be a little confusing, and let me reiterate. The binary molecular compound is not ionic. It is not made of ions. But the words from the anion is used for the second atom in the compound. So what is this? This is carbon di. What's the name of the ion from oxygen? Oxide. So this is carbon dioxide. Now, what if I change the formula just a little bit? What if I change it to be CO? Then this not carbon dioxide anymore. Now it's carbon monoxide. Notice I didn't write MONOOXIDE, right? Two O's in a row isn't going to happen. So it's carbon monoxide. All right, let's try another example. What about N2O5? What's that? Okay, let's do it all together. What's the prefix? I do need a prefix because I wouldn't use mono. There's another prefix. I use the prefix for two. So di. What's the atom name? It's nitrogen. Okay. What's the next prefix? Pent. Yep. And I'm not going to use the A because A's don't go before O's. So it's just pent. And again, it's an oxygen, so it's oxide. So this is dinitrogen pentoxide. Let me show you two more examples. And I'm going to make them similar on purpose. Well, what would be, if I could make this compound, I'm not saying that I could, what would be trichlorine? Oops. Trichlorine. Let's try this. I need a little more room. Trichlorine. Heptabromide. Let's write the formula down for that. Trichlorine heptabromide. Yeah, exactly. So Cl, chlorine, how many of them are there? 3. What's the formula for the atom that comes from bromide? That's Br. And how many of them are there? That's 7. I wanted to use this last example to show you how this changes. What if I do this? I'm not saying these are real compounds, but we can really practice naming them, even if they were. What if I just switch the position of the two atoms? Same numbers, but I just switch the position. How does the rules now tell me the name of the compound? Is it heptabromide trichlorine? It's not, remember, because this first atom is always the atom name. So now it's heptabromine trichloride. Heptabromine trichloride. Okay. All right, so, wow, that was a lot of nomenclature. And so I'm going to end it there. And if you now take a look at all of the videos on nomenclature, we've got like 3 hours, at least 2 hours. It's maybe getting approaching 4 hours worth of nomenclature at this point. That's a lot of nomenclature. At the end of the day, you got to know it all. And really the crucial bit is the nomenclature of the polyatomic ions. Everything after polyatomic ions revolved around the names and formulas of the polyatomic ions. So I'm going to leave it there.